Welcome to our first set of thermodynamics practice questions. In this video, we will dive into the properties of substances. Ensure you are referencing the FE handbook while answering these questions. As a supplement to this course, check out the full-length practice exams and other topic-specific practice questions that can be accessed through the link in the description. Now, let's get started with some thermo practice questions. A sealed container holds water vapor undergoing a vaporization process. At an initial state, the pressure is 150 kilopascals and the temperature is 350 Kelvin. When the temperature is raised to 370 Kelvin, the pressure increases to 198.5 kilopascals. Assuming the vapor behaves as an ideal gas and the enthalpy of vaporization remains constant over this range, calculate the approximate enthalpy of vaporization of water in kilojoules per kilogram. Use the following values for the ideal gas constant and molar mass of water. What is the closest values to the enthalpy of vaporization? We start by recognizing that this problem involves a phase change, specifically vaporization, and that we're given how the vapor pressure of water changes with temperature. Because of that, we use the Clausius-Clapeyron equation in its logarithmic form, which relates the change in pressure to the change in temperature during a phase transition. First, we plug in the known values as listed. We calculate the left-hand side of the equation, which tells us how much the pressure increased due to the rise in temperature. This gives us a value of about 0.28. Then we calculate the temperature-dependent term on the right-hand side. This term captures how sensitive the saturation pressure is to changes in temperature. This comes out to be approximately 1.544 times 10 to the negative 4. Now, we solve the equation for the molar enthalpy of vaporization. Doing that gives us approximately 15,086 kilojoules per kilomole. Since the question asks for the enthalpy per kilogram, not per kilomole, we then convert the answer by dividing by the molar mass of water. That gives us approximately 837 kilojoules per kilogram. Therefore, answer option B is correct. Practice question 2. A piston cylinder device contains a two-phase mixture of saturated liquid and saturated vapor water at a pressure of 200 kilopascals. The specific volume of the mixture is measured to be 0.6. At this pressure, the specific volume of saturated liquid is 0.0016, and that of saturated vapor is 0.8857. What is the quality of the mixture? We begin by recognizing that we're working with a saturated two-phase mixture of saturated liquid and vapor. The key variable we're solving for is the quality, which represents the mass fraction of the mixture that exists as vapor. Since the pressure is given and the system is saturated, we can use the specific volumes of saturated liquid and vapor to relate to the specific volume of the mixture. From the problem, we know that the specific volume of the mixture is 0.6, the saturated liquid volume is 0.00106, and the saturated vapor volume is 0.8857. By computing the difference between the vapor and liquid volumes, we find the change in specific volume to be 0.88464. Plugging into the relationship, we get a quality of the mixture of approximately 0.677. This means the mass fraction of the mixture in the vapor phase is about 67.7%. The final answer matches answer option B. Practice question 3. A piston cylinder device contains air modeled as an ideal gas. The system undergoes an isentropic compression from an initial state of 100 kilopascals and 300 Kelvin to a final pressure of 800 kilopascals. Assume the ratio of specific heats for air is K equals 1.4. What is the final temperature of the air after compression? We begin by recognizing that the process described is an isentropic compression involving an ideal gas, meaning the entropy remains constant throughout. In such a case, there's a direct relationship between the temperature and pressure at the initial and final states. Here, the given values are the initial temperature, initial pressure, final pressure, and a specific heat ratio. We first compute the exponent by subtracting 1 from K and then dividing by K, which is approximately 0.2857. Using this exponent, we take the ratio of final pressure to initial pressure, which yields approximately 1.913. Finally, we find the final temperature, which results in 574 Kelvin. Therefore, option C is correct. Practice question 4. A closed system of pure water at constant temperature and pressure undergoes a spontaneous phase change from vapor to liquid. Based on thermodynamic free energies, which of the following best explains why this process occurs? We start by identifying the appropriate thermodynamic potential. Under these conditions, constant temperature and constant pressure, the Gibbs free energy is the correct function to use when evaluating spontaneity. In thermodynamics, for a process to occur spontaneously under these conditions, the change in Gibbs free energy must be negative. That means the system naturally evolves toward a state of lower Gibbs free energy. Now, if we consider the phase change from vapor to liquid, this typically happens when the temperature is below the boiling point. In such a scenario, the system releases energy to the surroundings. This energy release causes the system to shift from a higher energy state, vapor, to a lower energy state, liquid. As a result, the Gibbs free energy of the liquid is lower than that of the vapor, and this transition is associated with a decrease in the overall Gibbs free energy of the system. This confirms that the change in Gibbs free energy is less than zero, satisfying the criterion for a spontaneous process. When we evaluate the answer options, we see that choice A is incorrect because Helmholtz free energy is applicable under constant volume, not constant pressure. B is correct. It states that Gibbs free energy decreases during a spontaneous process at constant pressure and temperature, which matches our analysis. C is incorrect because it suggests the Gibbs free energy increases, which contradicts the spontaneity condition. Finally, D is incorrect because Helmholtz free energy is not the governing potential in this pressure-controlled situation. So B is the only correct answer option. Practice question 5. A gas stored in a tank at 3.5 megapascals and 500 Kelvin behaves as a real gas with a compressibility factor of 0.85. The specific gas constant is 0.287 and the mass of gas in the tank is 2.5 kilograms. The tank volume is 0.8 cubic meters. What is the specific volume of the gas in the tank? We begin by identifying the relevant information provided in the problem. Next, we apply the real gas equation to estimate the specific volume. Plugging in the values gives us approximately 0.032 cubic meters per kilogram. However, the specific volume is defined as the total volume divided by the mass. So we take the tank volume of 0.8 cubic meters and divide it by the 2.5 kilograms of gas, which yields a specific volume of 0.32 cubic meters per kilogram. Therefore, answer option D is correct. Practice question 6. A chemical engineer is designing a system that operates at high pressures using methane gas. While reviewing the behavior of the gas in the system, she considers whether it can be treated as an ideal gas or whether real gas effects must be accounted for. The operating pressure of the system is 12 atmospheres, and the temperature is near ambient conditions. Which of the following best explains why the ideal gas may not be accurate in the situation? We start by recalling what assumptions the ideal gas law relies on. Ideal gas behavior is based on two key simplifications. First, that the volume of individual gas molecules is negligible compared to the volume the gas occupies, and second, that there are no intermolecular forces between the gas particles. These assumptions work well when the gas is at low pressure and high temperature, conditions under which the molecules are far apart and interactions are minimal. However, in this scenario, the engineer is dealing with a system operating at 12 atmospheres of pressure, which is considered high. Even though the temperature is near ambient, the high pressure causes the gas molecules to be packed closer together. As a result, the intermolecular forces between them, whether attractive or repulsive, becomes significant and can no longer be ignored. Under these conditions, the behavior of the gas begins to deviate from what the ideal gas law predicts. To quantify these deviations, we use the compressibility factor, Z. For an ideal gas, Z equals 1. But for a real gas under high pressure or low temperature, Z differs from 1, reflecting the influence of real gas effects. In this case, because the pressure is high, Z would not equal 1, indicating non-ideal behavior caused primarily by increased molecular interactions. Evaluating the multiple choice options, we can see that choice D correctly identifies the underlying cause. It explains that at high pressure, the molecular interactions become significant, which in turn makes the compressibility factor deviate from unity, thus leading to inaccurate predictions by the ideal gas law. That concludes our practice questions for this unit in thermodynamics. In the next lecture, we will continue with this topic and cover the laws of thermodynamics. Again, if you want more example questions or complete FE practice tests, visit the link in the description or on screen. Thanks for watching.